Hello everyone, my name is Sarah Gazani and I am with the Department of Mechanical Engineering of the University of Victoria and will present to you our work on a multitask approach to aerial depth completion and object detection. I would also like to acknowledge the funding of this project from the National Research Council of Canada under the grant agreement of AI for All 1292.
We know that 3D mapping and understanding of scenes are crucial tasks for uncrewed aerial vehicles that are responsible for large-scale inspections and condition assessments. While visually inspecting a target such as infrastructure for monitoring or 3D modeling purposes, it is crucial for the UAV to efficiently deploy its onboard sensors to acquire information from its surroundings to ensure a safe, collision-free travel while satisfying the mission objectives. One of the essential tasks carried out on board the drone is object detection for navigation, obstacle avoidance, and target identification. Meantime, for the 3D modeling purposes of an identified target, dense depth maps are required to achieve high-quality 3D reconstruction results. Using reliable LiDAR sensors that produce high-resolution 3D point clouds is an option. However, their measurements are typically prone to noise and put safety-critical decision-makings at risk. On the other hand, LiDAR sensors with higher performance guarantees may surpass the drone's payload capabilities and bring about power consumption problems. One of the popular methods to tackle this challenge is using depth completion methods to process low-density depth data and produce high-density depth maps. But why depth maps? Among the many ways we could represent a 3D model, using point clouds and depth maps are more practical for navigation and perception purposes. Depth maps are grayscale 2D images in which each pixel represents the distance of the sample in space from the scanning device. The problem with point clouds is that they are not structured and are difficult to handle and process, especially in real-time applications. We can use depth maps to parameterize the domain of point clouds, or in other words, we can consider point clouds as an embedding of a set of depth maps and store them depth maps instead of the point clouds. With this understanding, we can realize the importance of having a dense depth map and eventually the applicability of depth completion for 3D reconstruction purposes.
Depth completion is carried out in a guided or unguided manner. The first one is the image-guided depth completion, which relies on color images for guidance. The basic idea for the methods belonging to this category is to use the texture and the color information to help navigate to the nearly correct depth values from the known neighboring values in a depth map. The other one is the unguided depth completion, which uses the mere supervision provided by the depth data to complete the sparse depth map and is not in the scope of this work. In both traditional depth in painting and deep learning-based depth completion, sometimes features, or better to say, the change of the features across the scene are used to predict the depth of the missing or the noisy pixels to put the right values in place. As in one of the works in depth in painting, for example, the texture or the color changes in different directions are calculated to interpolate the depth values. In the deep networks designed for the task, a similar thing is happening, meaning the network tries to find the best and the most meaningful bottleneck which is most helpful for depth completion, and it is easy to see that that bottleneck being a geometric representation of the scene could be very helpful. Well, the question is, what geometric representation is best here? One of the most used representations is the map for surface normals. Another helpful representation is the object boundaries or occlusion boundaries, which helps the network to identify the boundaries, which are usually blurred out in the reconstructed depth map.
As mentioned in the previous slide, an important question is which representation of the scene or which features are helpful for the network to lead it to the best depth completion results. And some of the works answer that by guiding the networks to learn surface normals or object boundaries or other geometric representations. Our answer to that question, which at first was just a hypothesis, was that maybe those features could be features of higher semantic value. Features that could help us also detect and identify the objects in the scene. To test that hypothesis, we merged two different networks, which we call pathways, by using the same backbone with them, and let them share the features from multiple stages of the encoder. In this way, we guided the network to extract different intermediate features. Now these feature maps benefit both streams because they contain information that the partner stream was not capable of extracting. For example, the depth completion network by itself, especially for such architecture, tends to extract features that are more local to the pixels and are of less semantic value. But now, the network will learn features more unique to the objects present in the scene, and will see what the features of the objects should look like. And that is what helps it do a better job while filling the missing depth values. Apart from that, we use Monte Carlo dropouts to obtain a representation for pixel-wise uncertainty map at inference time, to experiment with the difference in the behavior of the multitask network and its single task counterpart. Here is the architecture for the network that we proposed. As I mentioned, we used the encoder-decoder architecture developed by the sparse paper. First, the sparse depth map and the RGB image go through separate convolutional layers, and then the feature maps are concatenated and go through several stages of encoding using res blocks. This part is the shared backbone of the network. The resulting feature maps is then upsampled, and using skip connections, features from the upsampling and downsampling stages are fused together. The features extracted from the encoder are also used as the intermediate features for the object detection pathway, which is the faster RCN network. This results in boundary boxes for the detected objects. We use the L1 norm loss function to monitor the depth consistency or the resemblance of the output depth map and the target depth map, and we also use the smoothness loss, which aims at suppressing the noises and ensuring local smoothness over the map, and it is basically a minimization of the L1 norm on the second-order derivative of predicted depth map. Also, the detection loss is utilized, which contains two terms, proposal loss and the final detection loss, which are summed with a relative weight. To implement our network, we use PyTorch Lightning modules, and we train the network on the aerial depth dataset. We also train this network using the NVIDIA GTX 360. Because the original dataset was not providing any annotations for the buildings in the scene, we manually annotated 1000 frames to provide supervision for the object detection pathway. Also, for the sparse depth maps, we uniformly sampled from dense target depth maps pixels down to 0.7% density of the overall pixels. Here are the input-output visualization of the network. Sparse depth maps of low density and RGB images are processed by the network to generate detected targets and denser depth maps. Here you can see a qualitative comparison between the output of the multitask network and the single task depth completion network. You can notice a difference in the object boundaries. The multitask network identifies comparatively crisp boundaries in areas where an object has been detected. The single task network, in contrast, predicts blurred depths. Again, as you can see, the depth values retrieved that belong to a detected object, which in this case are buildings, represent the object better, meaning the object is more observable and has crisper boundaries, whereas in the case of a single task network, the objects are more blurred out, and sometimes they're hard to notice. And here are the uncertainty map results. So these maps have been generated by activating 2D dropouts of the network at inference time and doing multiple forward passes, and each pixel here presents the variance of those outputs of the forward passes. As you can see for the multitask network, lower uncertainties or lower variances have been observed around structures, which is the opposite case for the single task network. As previously discussed, the introduced supervision enhances the shared backbone's ability to extract contextual information from inputs, leading to improved depth completion performance. To assess the robustness enhancement, we exposed both single and multitask networks to defective input depth maps. We subject the network to RGB images with sparse depth maps containing increased Gaussian distance dependent noise from 10% to 20 and 40%. Additionally, we introduce random boxes on the maps, resulting in missing depth values within the boxes. This tests whether relative depths of structures can be inferred even without their actual depth values. In both cases, the multitask network outperforms its single task counterpart, as can be seen in the two figures. In conclusion, our study addresses the challenge of sensor data defects affecting the 3D modeling and safety assurance of autonomous aerial vehicles. We have proposed and implemented a multitask network that effectively performs depth completion and object detection tasks. By leveraging semantic feature maps, we have improved the accuracy of depth completion results. Our network, utilizing a shared backbone with task-specific heads, generates both dense depth maps and bounding boxes for infrastructure localization. Comparative analysis demonstrated a superior performance of our multitask network, particularly in generating depth maps for object-detected pixels. While this work serves as a proof of concept, our future research will focus on exploring shared feature maps, expanding the annotated dataset for broader applicability, and investigating applications such as online view planning. The outcomes of our network hold potential for scenarios requiring target detection and precise depth information, crucial for UAV operations. Thank you so much for listening to this presentation. We would love to hear if you have any ideas or suggestions. Please do not hesitate to contact me, or if you have any questions, I would love to hear them and hopefully answer you. Thank you.